Okay, so just a quick recap. Everyone can see my screen, right?
Yes.
Yeah. So we looked at the LFP data, which is the low frequency component of the raw signal. And here's the evoked response. And we asked these questions. And in the last two classes, we have talked about the delta function and the convolution operation, which are sort of like the building blocks that is needed to answer some of the questions that we have asked. So, yeah, so we will start the Fourier analysis today formally. So in the last two classes, we have looked at continuous and discrete systems, and in particular, a time invariant and a linear system, LTI, which have nice these systems have nice properties which allow them to be analyzed properly. So we consider two types of basic signals, impulse functions, and we looked at the impulse response function, which is given by this. This is the response of the system when you give an impulse function as an input. And turns out if the system is LTI, then if you give any other input xn, the output is just the signal xn convolved with the impulse response function. Okay, so this is what we did in the last class, and this is true for both continuous and discrete systems. In a continuous system, this becomes an integral. So this is the convolution in continuous domain, and it's indicated by this symbol here. Okay, and that's what we have done. We looked at some of these things, not in too much detail. These are quite straightforward. And now we are looking at the second type of basic signal, which are complex exponentials. And the reason why these are interesting is because if you give a complex exponential as an input to LTI system, the output is also the same complex exponential, just multiplied by some number. Okay, it's a complex number, so it has an amplitude and a phase. But basically, if you give a sinusoidal signal, you will get the same frequency back. You can't get a triangular function or some delta. You can't get anything else if the system is LTI. So in linear algebraic terms, complex exponentials are eigenfunctions of LTI systems where this factor is the eigenvalue. Okay, so this is where we had stopped in the last class. So are there any questions before I move on? Okay, so let's look at the proof here. The proof is actually very straightforward. Suppose my signal is e to the power st and I want to look at the output. So I'll just say that it's an LTI system. So the output is just the transfer the impulse response function and the convolved with xt. So this is the formula in the continuous domain. This is the formula in the discrete domain. And you just put x as e to the power st. So here it's just e to the power st minus tau. And you can see that e to the power st will just come out of this because this is integration is over tau. So t is a constant here, so is s. So this just comes out and you're left with this. That's it. Same here as well. Okay, so this is z to the power n integral of this. And therefore, as long as this guy exists, if this integral converges, the output is just e to the power st multiplied by this number hs, where hs is given by this. I've just written this term here as hs. But the point is that the output is just e to the power st, same as the input, just multiplied by some number here, which is given by this. Okay, so the proof is very easy. You give this as the input, you get that as the output. Okay, same thing holds in the discrete domain also. So we will see that when we talk about the Fourier analysis, this is just a simple form of an exponential where this s is just j omega. If you don't do it and just work with s, where s could be not j omega but some other number, you have a more generic form of transform, which is called the Laplace transform. So we won't talk about Laplace transform. Fourier analysis is actually a sort of subset of Laplace transform, but Fourier analysis is so popular that that is what people eventually focus on. And we'll see the reasons why that is the case. But in general, this thing holds for any type of complex exponential. It doesn't have to be a unit, e to the power j omega t. It is true for any e to the power st, okay, where s and z are complex numbers. Okay, is this fine? So now here's the thing. I know that if I give an complex exponential in the continuous domain, I'm going to get a complex exponential out. Now I want to know in my real world, the signals are in general not complex exponentials, right? They could be anything. So I asked this question that can I decompose my signal as a sum of complex exponentials like this? Xt, this is not a complex exponential. This is anything that you can think of. But can I always decompose it as a bunch of complex exponentials? Why do I want to do that? Because if I can decompose it this way, I will always know what the output is. It's just this. All I'm doing is, this is because of linearity, right? So the output of a single exponential is this. Right? So if I just give e to the power skt, I'll get h sk e to the power skt. That's my, that's just falls from here. And then this scaling will add the same scaling, summation will add the same summation because it's linear. So my yt is known for any xt as long as I can divide it, decompose it this way. Okay, and that is why Fourier analysis is so popular, because what is it at the end of the day is just a way for you to decompose any signal into a bunch of, a summation of, or an integral of complex exponentials. Okay, so again in linear algebraic terms, now these are my basis functions. You have to make sure that these constitute a basis function, which means they span the entire space. But then if you decompose it in terms of these basis functions, then the output is easy to get, because these basis functions happen to be eigenfunctions. So the output of these basis functions are just the same functions back, just multiplied with the some number here. So as long as you know h of sk, you're done. You can then find the output of any input. And this is what we try to do in Fourier analysis. Okay, if there are any questions, please stop and ask. Okay, so now the question is, can I always decompose any signal as a bunch of exponentials? And the answer, surprisingly, is that in most cases it is yes. The form changes a little bit depending on whether the signal is periodic or non-periodic or aperiodic. The form also changes whether it's discrete or continuous. But these changes are, sort of heavily interrelated with each other. So it's very important to sort of be aware of these slightly different forms of Fourier analysis for different types of signals. So we will start off with the simplest type of signal, which is a periodic signal. It's a signal that keeps repeating itself, like a sinusoid, for example, or a triangular wave or a rectangular wave that keeps coming back. So we will start off with that, and we'll talk about Fourier series. Then we will talk about the discrete version of it, the discrete Fourier series. Then we'll talk about the aperiodic versions of both the Fourier transform and DTFT. And you might be left wondering why this continuous case has 2 while the discrete case has 3. And the answer will become clear towards the end when we talk about discrete Fourier transform. Okay, and at the end of the day, when everything is said and done, when you have your data and you are doing the Fourier analysis in MATLAB, you are always doing DTFT. You can't do anything else really. I mean, the fast Fourier transform is just a fast way of implementing the discrete Fourier transform. So all this build-up of theory will eventually be for us to understand what the DFT is. It's basically just, well, we'll see. Let it evolve in an, in a principled way. But essentially, at the end of the day, we are implementing DFT. We are computing the DFT using some fast algorithm. So it's called the FFT program in MATLAB. All right. So now let's get to first a periodic signal. And this takes us to the domain of Fourier series. Okay, so what's a periodic signal? Let's talk about the continuous case now. So it's a signal X which repeats itself. So X of t plus capital T is just xt. Okay, so this is quite straightforward. Now here's what we do. You consider a set of harmonically related complex exponentials phi kt, which is of this form. So it is e to the power st, but in this case s is just an imaginary number. It's jk omega. Okay, so maybe I'll just 1 second. So just to be clear here, let me just write down. This should be, I think, familiar to most of you. But so e to the power j omega is can be or j theta or whatever is can be written as cos omega t plus j sine omega t. Okay, so and there's a complex conjugate that we will see later. It's a conjugate. So if you've got a complex signal x, which can be written as some type of a e to the power j theta. So this is then its conjugate is a e to the power minus j theta. So this is the amplitude and the phase. Or if you write it as a real term and a complex term, its conjugate is this. Okay, so you can find all these relationships. Your this can be written as a cos theta plus j a sine theta. So any complex number can be represented as an amplitude and a phase and it can be then represented as a vector with an angle theta or an amplitude of a, or likewise with a real value of a and a complex imaginary value of b. So this is the real axis and this is the imaginary axis. Okay, I'm hoping this is familiar to most of you. This is, I think, just wanted to have these things cleared before I move on. Right, so this is fine, right? Any questions? So any complex number can be written either as an amplitude and a phase, or as a sum of, a real number and an imaginary number, I is the imaginary constant, and just to, so what is e to the power, by the way, so mathematicians write I. Okay, so mathematicians write the complex is as I. Engineers write it as J. So I am an engineer, so I will write it as J. Or rather, I was an engineer. Mean the same thing, obviously. It's just nomenclature of sorts. So e to the power I pi. What is that? What's e to the power I pi?
Minus I.
Minus 1.
Is cos pi plus I sin pi, right? What is cos pi?
Minus 1.
What is sin pi?
0.
0, right? So e to the power I pi plus 1 is 0. So there is a guy, this is Euler's formula or theorem or something. So there's a guy in who records brain signals from mathematicians while showing them equations. Okay, and see their reaction. So this is a very famous equation. This relates 4 fundamental constants, e, pi, 1 and 0. Okay, so and the finding is that mathematicians love this equation more than any other equation in the world. Okay, and he, if you listen to that guy's talk, you would say that you would see mathematicians just shaking in delight when they see this. There is such an elegant, such a beautiful relationship between these very different fundamental numbers, 0, 1, e and pi. That this nice relationship which just sort of links them together is just like the most beautiful thing that they can think of. Apparently, one of Ramanujan's expansions, where he has like pi is 1 plus something 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 something, that's like the worst one, which mathematicians don't like. So this is based on their brain signals and behavioral reports and so on. But this one is the clear winner. Okay, so yeah, that's our complex representation. So I will be using both types, either dividing them as cos and sines. So I can either call it just a complex exponential like this, or equivalently say that I'm going to divide it as a bunch of cosines and sines. Both are equivalent representations. And we will stick to this, but it's easy to go back and forth. Okay, so I'll head back to where I was. So this is my basis function now. So I'm going to say that, okay, I'm going to now try to divide my signal as a linear combinations of these functions. Notice that here omega naught is just 2 pi by t. So this is the fundamental frequency. And as I'm increasing k, it's just this fundamental frequency is increasing. Okay, well, when k is 0, it's just a constant 1. When k is 1, it's 2 pi by t. When k is 2, it's twice the frequency. And so on. Okay, so each of these signals has a fundamental frequency that is a multiple of omega naught, and therefore each is periodic with t as well. In fact, the higher ones are a fraction of t, t by 2, t by 3, t by 4, and so on. So if I've got a signal which is defined as a sum of these, it's also going to have a period of t. Right now, the question is, if x is any periodic signal, can I find a bunch of AKs such that xt is the sum of these? Okay, and the answer is yes. It's actually very straightforward. I say that x of t is this. I multiply xt with a number here, which is e to the power minus jn omega naught t. I will tell you why we are doing this in a bit. But then the same number gets multiplied here. And then what I'm going to do is I'm going to integrate both sides from 0 to t like this. Okay. Why are we doing this? Because essentially now ak is, the integral is over dt. So the integral just comes in. So I just have to evaluate the integral. So let's look at this and let's try to understand what this is going to be. The answer is right here. But I will just go back and do this. So I'm going to integrate from 0 to t, and I have got e to the power j. Let me just think of k minus n as some one number. Let's just call it e to the power j. Oh well, I'll just keep it like this only. E to the power j k minus n omega naught t. Oh, sorry. Okay. So when k is equal to n, what does this become? When k is equal to n, this is 0. So what do I get here?
T.
It's just
D.
t, right? So this is just integral of dt over 0 to t. So it is just t. This is straightforward for k equal to n, right? What if k is not equal to n? So it's easy to see that if I decompose it into cos k minus n omega naught t plus j sine k minus n omega naught t over an entire period. So the cosine function will look like this. This is some number, right? So this is not some fraction, it's a number. It's either 1 or 2. So cos omega naught t will go from like this. 2 will be twice that, right? So there will be 2 full cycles there. Three will have 3 cycles, 4 will have 4 cycles. So likewise, the sine omega naught t, this is sine omega naught t, this is sine 2 omega naught t. Sine 3 omega naught t will have 3 cycles, 4 cycles, 5 cycles. But whenever you integrate it over the entire period, it's always 0. Because whatever positive you have, the negative side takes care of it. So the integral over an entire period of either a cosine or a sine is just 0. So this is it. It's as simple as that. So this is a very useful concept. Let me just also think about this in terms of a discrete counterpart. This is a concept that I will later just discuss in passing. So if I say I am going to have a one vector like this, so I'm going to sample the unit circle using equispaced vectors. We will see later in the discrete case, this is how the basis functions look like. So if I'm sampling this space, which is 2 pi, 0 to 2 pi in 2 vectors, the 2 vectors will look like this. If I do 3 vectors, oh gee, sorry, I have a pen that is hard to maneuver. So get back here. So then they will be 120 degrees apart. If I divided it into 4 vectors, it's going to be like this. As long as I am sampling the this angle 2 pi into an equal number of equispaced vectors, the sum is always 0. Okay, so the sum of equispaced complex vectors. When I say equispaced, it's equispaced in your this angle axis. It's always going to be 0. And this, what we are seeing right now, is just the continuous version of the same thing. The integral of complex exponentials is 0. Okay, so any questions on this? This is straightforward, right? Everyone happy? Okay, so assuming the answer is yes, I have got my an. Okay, because when I do this integral, it comes out, it's always 0. The only time it's not 0 is when n is equal to k. So in the summation, all the terms go to 0 except an. So this is just an multiplied by t. So an is 1 by t, integral of 0 to t, this. So lo and behold, I have actually found the coefficient that I was looking for. And this is what is called the discrete Fourier series. If the signal is periodic, I can decompose the signal, any signal. It could be a triangular wave, it could be anything. This doesn't have to be a sinusoid. But it can always be decomposed into a bunch of essentially sines and cosines. Remember, this is just cos k omega t plus j sine omega t. So I can decompose any periodic signal into a infinitely large number of either complex exponentials or sine and cosine functions, which are multiples of the fundamental frequency of x, like this. So, and then ak is given by this formula here. It's just the integral of xt given by this. Okay, so this is a continuous signal, but the Fourier series expansion is discrete in the sense that, well, it's not discrete in that sense. The Fourier series is not an integral, it's a sum. So there are an infinite number of sinusoids that are required, but those sinusoids are in this case countable. It's, sine of omega t plus sine of 2 omega t plus sine of 3 omega t and so on, each multiplied with some amplitude and shifted by some phase. But that's it. That's it. So we can always decompose a signal into a bunch of these complex exponentials. This is what we were looking for in the beginning. And therefore, it's very easy to find yt also if you know how each complex exponential is modified when you pass it through the system. Okay. Any questions? This is the Fourier series. By the way, so there's a very interesting story here. So there were, quite a few people who were looking at these kind of expansions. This was mainly related to heat transfer and all that. So, but many people thought that, it's not possible for you to expand a function which may not have which may not be smooth as a sum of functions that are smooth. Okay, so sinusoids are smooth functions, right? So I can what I'm telling you that my function could be even something like this. Now the derivative doesn't exist here, or the function, these are all periodic functions, right? And I'm saying I can always find a bunch of sinusoids whose frequency is essentially, so if this is the period t, so then this is also t plus twice of that 2t, 1 by t is the frequency, then this is 2 by t, 3 by t. These are my these are, well, real, yeah. But if you add a phase and add an amplitude, essentially then it's just a scaled and shifted sinusoid. I add them up and I can get back my signal. And this could be anything. As long as it's periodic, it's fine. It could be anything. So back in the days, people didn't like this idea that something that changes and has a discontinuous, the derivative is discontinuous. How can it be represented by functions that are just changing so smoothly? So when Fourier did this analysis, the paper was sent to, like real stalwarts of the day, involved Laplace and Lagrange. You guys may have heard of Lagrange multiplier and Laplace transform and all that. Kind of amazing to live in an era where you send a paper and it gets reviewed by, these giants in the field. But one of the guys who didn't like this idea just wouldn't let this paper publish. I think it was Lagrange, but I think it was Lagrange, but I could be wrong here. And so Fourier's work actually was not popular for a long time. It took him like 15 years or some ungodly amount of time to get his idea across. Okay, it's very sort of interesting anecdotally that today Fourier is everywhere, but back in the days he struggled to get this. I think to his credit, so many people got to till this stage. It was not just Fourier, but Fourier was able to expand his idea to the continuous domain also. So that's the Fourier transform, which was a significant step forward. Okay. Any questions on the Fourier series before I move forward? Okay, I'll take it as a yes then. So let's move forward and let's look at a couple of examples here. Xt sine omega t, just a sinusoid. How do I represent it as a sinusoid? It's very easy. I can look at sine omega t as a sum of two complex exponentials, right? So, oh, I think I can write here also. Let me try to see if I can write here. Yeah, so e to the power j omega t. Now, this is nice. Is cos omega naught t plus j sine omega naught t, right? And e to the power minus j omega naught t is just that, minus j sine omega naught t. So when I subtract them, this cancels out and this becomes plus, so it becomes 2j sine omega naught t. So when I divide, this gets cancelled out and I get sine omega t, right? So now if I look at my original formula here, in this case, it's very straightforward. The answer here is A1 is 1 by 2j. A1 is the coefficient related to ej omega naught t. Ej omega naught t. So that coefficient is 1 by 2j. Minus 1 is minus 1 by 2j. Everything else is 0. So I can think of a way of writing the Fourier series as an axis here. So this is k now. And I will be just putting 1 by 2j here and minus 1 by 2j there. And everything else is 0. Okay, so obviously I can't put a complex number here. So I usually have an amplitude spectrum and a phase spectrum. So it's easy to see that the amplitude is the same here. It's half. And the phase is just opposite of each other. So for any real signal, as we will see later, the amplitude spectrum is symmetric and the phase spectrum is anti-symmetric. Whatever is the phase on this side, on that side it's just the opposite. Okay, and it's true for any real signal, as we will see later. Okay, so this was a trivial example. If I have got a single sinusoid, then as you might imagine, it's represented in the Fourier space by just a single point, because that's all you've got. So I've got one, sinusoid here of frequency omega naught by t, 1 by t or omega naught. And one complex exponential here, whose phase is the opposite of what we have here. So when you add them up, you get the real signal back like this. Here's a more complex example. So we will actually keep coming back to this example. So let's pay attention here. This is a periodic signal. This is a periodic signal. It's what's the period here? It's t, right? You can see it repeats from here to here, or well, for that matter, you can take any length and it repeats. But within that, up to t1, it takes a value of 1 and then it becomes 0 for the remainder of the period. So if I look at my Fourier coefficients, now the integral, instead of being 0 to t, or minus t by 2 to t by 2. It doesn't matter which, as long as you're integrating over one period, it's the same answer. So I'm integrating between minus t by 2 to t by 2, but it becomes minus t1 and t1 because otherwise outside of that it's 0. So this is a0, and for any ak, if you integrate it this way, and you can find out that this is what the integral is going to look like. This is the same thing that we had done here, so I won't repeat it. But this is the Fourier output of this signal. Okay. We later see that this comes with a fancy name. It's called a sinc function. But here are, this is again taken from Oppenheim and Wilsky. These are scaled Fourier coefficients. I'm plotting t times ak for 3 different values of t. Here it's 4 times t1, 8 times t1, and 16 times t1. Okay, so when it's 4 times t1, then when it becomes 8, it's essentially becoming a thinner, and 16 is even thinner. So essentially the duty cycle is reducing as you go from here to here to here. Okay, and what we will see very interestingly as along these lines is that you can think of them as regularly spaced samples of the continuous envelope given by this formula, where the spacing between the samples 2 pi by t decreases as t increases. Okay, so this is where things will eventually get sort of confusing. So you guys have to really stay sharp here, because when we talk about aperiodic signals, we essentially think of it as a periodic signal whose period is infinitely long. Okay, so it repeats, but repeats after an infinite amount of time. So it's as well, it's the same as not repeating at all. And then it's essentially going to be an envelope whose samples are just infinitely close to each other, and from a discrete representation it will become a continuous representation. Okay, so then instead of AKs, I will have A of F. There will be a sample at each frequency, and the Fourier series will become what is called a Fourier transform. Okay, so just keep that in mind as we go through this. Okay, so right now this envelope of regularly sampled envelope of this is just coming from this formula. It's 2 sine omega t1 by omega, but you have put omega as this discrete sample as omega naught by 2, I suppose. Okay, so or there's a pi here, so it's 2 pi by t. Yeah. Okay. Is this fine? Am I losing people here, or is this okay? I can't see you guys, so please let me know if this is fine. If you are, it's okay, right? Some of you can say yes. Then I'll move forward.
So in the last equation means there has been rearrangement, right? So like
Yeah. So this rearrangement where instead of omega naught you write 2 pi by t, that will keep happening.
okay.
Okay, so all you have done from going from here, are you asking going from here to here?
Yeah. So means like every time we just use 2 pi by t, or like means, it's a
You can use either one. It's the same thing. You either write it like this or like that.
Okay.
Okay, so if you write 2 pi by t, the 2 and 2 will get cancelled, the t and t will get cancelled, and you'll be left with pi. It actually is more confusing than it seems. Often, you're looking for what happened here and there. So, And this will keep happening more and more as we go forward. So as I said, you have to really pay attention and stop and ask if something is confusing you. Okay, folks. So Fourier analysis is, amazing in a lot of ways. And one reason is that it has incredibly nice properties. So when we learned Fourier analysis, we would spend a lot of time talking about each of these properties. I will go through a few of these. I think the coolest property, well, they're all sort of cool, but this one is very cool. It's that Fourier transform converts convolution into products. And the Fourier transform of a product of two signals is the convolution of the coefficients. Okay, so it's a transform, and we'll see that this will hold for a Fourier transform as well. If I convolve two signals in the time domain, it's the same as taking the product of the Fourier transforms of those signals in the frequency domain. Okay, we will prove this. Let's see if I have time to get to that. Otherwise, I'll prove it in the next class. All these proofs are there in Oppenheim and Wilsky. So please go through this. Let's look at a few easy ones first. Linearity is okay, right? This one is straightforward. You can see that everything is linear in this equation. So if I do axt plus byt and add it up, all these coefficients are just going to get scaled and get added. This whole thing is linear. The integral is linear. If I integrate over axt plus byt instead of xt, the integral is just going to go over, right? So if this is becomes aht ht plus bmt, then you can see that this integral will come here, and when I integrate this, it's just a times whatever is the Fourier transform of Fourier series of h plus b times whatever is the Fourier series of m. I'm just representing them as this right now. Okay, so this linearity is easy to see, right? This should be quite straightforward. So Fourier transform is linear. Time shifting is also easy. You can see in this, let me just do the time shifting one. So I want to know the relationship between the Fourier series, Fourier coefficients of xt and a shifted version of x. Xt shifted by t0. Okay, so let's look at time shifting. So this is ak is 0 to t 1 by t e to the power xt e to the power j k omega naught t. What I have done is written this formula. Sorry, I forgot the minus here. And I say, okay, I'm going to find now, so my yt is just x of t minus t0. So what is bk going to be, which is the Fourier coefficients of yt. And it's straightforward. You put this in x of t minus t0 k. And here you just put this as t minus t0 plus e to the power j k omega naught t0 bt. And notice that this thing will just come out. So I have just done a minus t0 and a plus t0 here. That's it. Okay. So this thing pops out, and the rest, because this period of integral doesn't matter, is just your previous AK. So all I have done is now got a scaled version of the um, uh, uh, sorry, I've got the same coefficient. It's just multiplied by this function here, which is going to just change its phase. Okay, so in time domain, if you have a shift, in the frequency domain, it's just the same coefficient whose phase is getting shifted. Okay, is this fine? Sorry, so this is t minus t0 plus t0. There's a minus here, so this is where the minus is. Is this okay? So when I look at the Fourier coefficients of a shifted signal, it's the same coefficient as the original signal, just getting multiplied by a complex number here whose magnitude is 1, and this is essentially just adding a phase to this. This is a vector who's got an angle given by this, but otherwise it's a unit vector. So the amplitude doesn't changes, it just shifts the phase. Okay, and this one, the frequency shifting, is essentially the equivalent of this. If I multiply the signal with a number, this signal is just changing the phase of the signal by some m omega naught t. In the frequency domain, the Fourier series coefficient just corresponds to the shift in the frequency domain. So these two go hand in hand. Shift in time corresponds to a phase shift in frequency, and a phase change in time. Multiplying the signal with a e to the power j omega naught t is just going to change the, it's just going to shift the coefficient in the frequency domain. I leave this as an exercise because it's the same analysis that's done here. Okay. So likewise, it's very easy to see what happens when you look at the conjugate. So I've run out of, how do I now erase this? How do I can discard all of this. Good. So I'll come back here and look at the coefficients. Integral over t, and it's again, so if I'm now looking at coefficients of bk for a signal which is given by this is the complex conjugate. J k omega naught t dt. you can see that if I did a conjugate on this whole thing here, so if I had looked at AK conjugate, the conjugate will come inside, become the conjugate of this, and this is just going to make this plus. Right? I told you the conjugate just changes the sign here, but this can be now looked at as e to the power minus j of minus k omega naught t dt. So this is the minus kth coefficient of B. So Bk is just A star minus K. If I take the conjugate of the signal, the coefficients remain the same, but they get flipped in the frequency axis. Instead of K, I'm looking at minus K. And instead of the real, instead of the original coefficient, I look at its complex conjugate. Okay, so I will leave the remaining ones to you. I just wanted to show this periodic convolution, multiplication, and this Parseval's theorem. So this is a bit of a homework for you guys. I don't want to go around and do all of these. They're all straightforward, but extremely useful. So this table is very important. When we were undergrads, we would mug up this table properly and just do these over and over again. So please take your time and do this. We will be now moving forward and looking at different variants of Fourier analysis. They all will come with a table that looks just like this, and there are actually minor changes because they're all interrelated in some very interesting ways. So I would really urge you here to spend some time and go through this section and make yourself comfortable with what is going on here. They're all straightforward. The proofs are all straightforward, except a couple which I will go through. But then after this, we are going to pick up some pace. Okay, so I'm done with class. As always, I will take questions now and stop the recording. Discard.